Hello and welcome to this lecture where I will be discussing some little surprises in the physics of space travel from Newton and beyond. To do that, what I will show first is this nice video by the European Space Agency where they summarize with a little animation the travel and journey of a probe called Rosetta where it was sent off, in 2004 from Earth, and then eventually reached its target in 2014. Now, I will use this particular mission as a silver lining in order to touch upon some of the key points having to do with space travel and what type of things or physical phenomena people use to make these probes, satellites, and spacecraft travel. So just let's have a look at the end of the mission. So here we are already 6 years into it. Right, so that's it. I will stop at this particular point here. So here you saw with an animation the actual travel and so on. Now what I want to focus on is the actual data and the milestones, steps or stages of the travel that had to be taken care of by various maneuvers and so on. Now, the way I would present them is I will imagine that I have access to some space Google map in some future in my browser, and I'm asking Google Map, okay, I want to go from the Earth to this comet 67P, and how do I do that? And so Google Map will tell me this, okay, it will show me on the map this blue path, which is a path I have to take, and then some milestone steps here and there. I know the total amount of time that I've got to spend, which is estimated at least, which is 10 years and 2 months, and the actual total distance to travel. And I know as well what are the various routes that I've got to take as well. And I will discuss this as well in detail. Now, the very first question that I want to ask, which appears to be very, very simple, is simply this very first step, depart from Earth. My question is very simple here. What does it mean to actually leave Earth? So, of course, the question seems stupid because if I look at, for example, this little video game and I imagine that I'm this little character here and I'm discussing with my friend in his bedroom, here in this drawing, the walls of the bedroom are represented by this square here, outside of which there is pitch black, right? Now, if this player wants to leave the bedroom, he goes via the stairs and then he leaves them, and then he can also exit the house. And it's obvious that you exited the house. Why? Because there is not anymore any black, pitch dark color, and also because you are outside of the walls of the house, and therefore you know you're outside of it. So that's the first thing to notice. Okay, you can leave your house, you know that because you are outside of the walls of it. Now, you can also leave something else, like a city. So I can leave Lincoln. Here you see a map of Lincolnshire, so you can leave Lincoln the city, and you can leave Lincolnshire as well. Why? Because it has well delimited borders. At a bigger scale, you can also leave a country and go to another country that is next door or somewhere else, and that's because, again, there are well-defined borders. Of course, you might not know them, but some people do. Okay, so there are borders in countries, and therefore there are well-delimited borders. Going outside of it makes sense. But if we are looking at something different here, for example, this little ball over there, let's assume here that this is a cartoon of the Earth that is alone, if you will, among the stars. And the question I'm asking is, well, what does it mean to leave, for example, here, the Earth, when we know that we are already outside of it, right? So if we say that the Earth is a sphere, for example, we actually live on the surface of it. So we are already outside of the sphere. So why is it that we actually can't say that we have already left Earth? So to have a look at this particular question, let's zoom in. So let's assume we are on a space craft or space shuttle, and then we try to go towards the Earth, and eventually we'll land on Earth where we see fit, so that we can make little experiments. Okay, so here we approach the Earth, and then at some point we'll simply land. So this is a cartoonish Earth, of course, with a very small curvature, and then we have landed here. Okay, so the question here is, what does it mean to actually leave? So one possibility is to say that we just need to detach from the surface of the Earth. As soon as we detach from it, we can say we have left the Earth. The issue with this particular statement is that we know by throwing, for example, a ball up and down, I mean up, and then we'll see that it goes down like this. So if I throw a ball, it will do this, and then eventually it will simply fall down. Okay, and so what that shows is that if I throw something, even like the best baseball player, they throw a ball and then eventually it falls down on Earth. So it leaves the surface indeed, but ends up being pulled back by Earth itself. Okay, so it seems that there is no way to actually leave the surface of the Earth, even if for some time you can be detached from it. So, as an anecdote and an actually important metaphor here, I want you to recall, how do we call a place one cannot break free from? And of course, probably something has popped up in your mind, and I believe this has to be a prison. Okay, and indeed, in this context, because there is no way apparently to detach really from the surface of the Earth, at least for a long time, then it appears that, well, this is as a prison. And in fact, the vocabulary employed in physics and astrophysics has to do with the notion of escaping from Earth or from other celestial bodies. So, of course, if we want to know how we escape from there, we can try to find some answers in people who have written in the past about leaving Earth to, for example, reach the moon. And so one of the earliest examples, at least of the modern examples, is that of Francis Godwin, who wrote a very famous book called The Man in the Moon, which is allegedly one of the first Anglo-Saxon science fiction writings, where a man is basically traveling to the moon using a swan chariot. And it actually describes quite in detail the travel from the Earth to the moon. And in the left page paragraph, what he explains is that the actual attraction from the Earth is basically similar to that of a magnet attracting iron. All right? And what he adds, and that's very interesting, is that provided it is within the reach of the attractivity, if you will, of the iron. And so here that would be provided we are within the reach of the attraction of the Earth. Now, this is also in relation, or this is further emphasized on the right page, where he says basically that after the time I was once quite free from the attractive beams of the tyrannous lodestone of the Earth, till my arrival in that new world of the moon. And so the idea here is that there seemed to be basically a distance, okay, where if you go beyond this distance away from the Earth, then you are basically free from it, okay, free from its attraction. Now the issue with an idea like this is that it basically assumes or proposes that there is a ceiling somewhere. Maybe that could be the limit of the atmosphere, however you would define that, or an invisible wall somewhere. The issue with this is that after this gentleman came Newton, and Newton came up with a fantastic, all-encompassing framework and universal law, which is that of universal law of gravitation, where he said that I deduced that the forces which keep the planets in their orbits must be reciprocally as the squares of the distance from the centers about which they revolve. Now, what he means here is that the forces that keep the planets orbiting around decay as 1 over the distance squared. Now, he adds, and thereby compares the force requisite to keep the moon in her orb with the force of gravity at the surface of the Earth, and found them to answer pretty neatly. What he means here is that the force that keeps the moon in orbit, okay, detached from the Earth, but in orbit, is the same that is keeping us at the surface of the Earth. So the lessons, if I want to emphasize this, is first, the force which binds us to the surface of the Earth is the same that binds the moon in orbit around the Earth. And the second one is that this force is universal between any two bodies and decreases with the square of the distance between their centers. What that means is that if you go far away, the force will be, let's say, 1 over a distance squared, and this distance might be very, very big. So the force will be very, very small. However, because even if you go like light years away from the Earth, 1 over light year squared is a very small number, but it's not a zero number. So what that means is that the force of gravity from Earth gets smaller and smaller, but is always non-zero, no matter how far we go away from it. So if freedom is to be defined as the total absence of any attraction force from the Earth, then it's basically an impossible challenge to be free from the Earth. But is it really nothing we can do about this? Well, it turns out that we have been a bit picky when we set our definition for freedom. Okay, we don't need actually the pull from the Earth to be zero to claim to be free. In fact, to be free, you could argue it's enough to be able to go however far you want from the Earth, including infinitely far. And if you can do that, then you're free. So to detail a little bit how that works, I will put forward an interpretation of what a force does that is called the monetary or economic interpretation of forces. Now, forces can actually be interpreted as compelling a monetary transaction for an object to change place from one place to another, basically. So let's assume that you've got an object that is at place A and it wants to go at place B, or it's going towards place B, if you will. Then it can only successfully go to place B if he's able to pay a particular amount of a particular token. Now, just to tell you that this is serious stuff, I'm not trying to mock you or dumbing down what forces are about. There is this now quite famous paper written by Juan Maldacena, who is a theoretical physicist, and he has written this paper basically where he proposed to rederive the Higgs boson and all the so-called gauge symmetries and gauge fields from the economic analogy that I'm talking about here. It's of course slightly different and slightly different rules, but that's basically the idea here. And so here we will just do a baby version of this in order to find out what does it mean to be free, essentially, from Earth. So you could argue, what is the money being exchanged here? So I'm telling you, you exchange some token and then you can move successfully or not toward place B. Well, this particular money is actually what is called the energy allocated to motion. Now, some of you may have some idea what is this, the name of this thing. but in case you don't know, this is called the kinetic energy. The way it reads is quite simple. This is, by the way, the only equation of the talk. So Ek is half mass times velocity squared. Now, mass is something we know very well. We carry them all the time, we weigh ourselves to determine our mass, so this is something quite neat and easy to understand. Velocity as well. We are very familiar with the concept of velocity. We've got now pedometers who measure our velocity for walking, for running, and then of course in our cars and bikes and stuff. And so basically all these two concepts, which are the two concepts that are needed to build kinetic energy, they are very familiar to us. And so that's very good indeed, because this is what we'll be paying and talking about when we talk about getting freedom. So what I want to do now is to look at the actual price or cost that one has to pay, and in particular one object that weighs 1 kilogram that would have to pay in kilocalories for every 10,000 kilometers that he has to move away from the Earth. Okay, so for every 10,000 kilometers that the object moves away from the Earth, he has to pay a particular cost. And I want here to display this particular cost and see how it looks, and whether whether the total bill is high or not. So for the first 10,000 kilometers away from the Earth, the actual cost for this is 9.10 kilocalories. If you want to move some additional 10,000 kilometers away from the Earth, then that would be 20 more. If you want some further 10,000, that would be 0.98 more, and then 0.55, and then 0.36, and then 0.25, and then some additional again 10,000 would be 0.18. Now you could continue this game up to infinity, and if you were to add all of this cost, it turns out that you end up with a finite amount to pay, which in this particular case would be estimated to about 14 kilocalories. And so this particular number is very important, because for an object of 1 kilogram, it tells you that you're in a prison, yes, but if you go fast enough so that you are able to pay the actual cost of freedom, then you're free. You're free to go, and you can basically go infinitely far away from the Earth and do as if the Earth basically did not exist as far as distance goes, right? So that's the first point here. That's the idea of the cost of freedom to pay in order to leave the Earth. Now, once we have said that, you can ask yourself what is the actual velocity that is required in order to escape. Now, it turns out that this particular velocity is independent of the mass of the object, so much so that for every object, then the velocity to escape from Earth is 11,123 meters per second, which is quite a big number, you may say. But also, one of the things that we can ask is that for celestial body of the mass of Earth, it will only depend on the radius. So the escape velocity depends only on how far you were from the center of the Earth, if you will. So one of the things we can play at is to set various copies of the Earth, but not just smaller version, but then with the same mass. So they would look like this. Right? So imagine these balls or these globes, they are all of the mass of the Earth, but then various radii that are written here. And so you want to know what are the actual escape velocities for these guys. Now, for the first one, that would be, of course, the one we just saw. So it's 11,123. For the second one, because the mass is denser, then this would be 35,174 meters per second. And then of course the last one is very, very dense, and of course the force associated to that is very strong, and therefore the escape velocity there is 351,740, and it turns out that this is a big number, okay? And this is a big number that was pointed out by Pierre-Simon Laplace in 1799, where he figured that you can have such so small planets that basically the escape velocity would be larger than the speed of light. And if that's the case, then that means that these particular celestial bodies would actually be invisible. They would not shine any light because light would not be able to escape. And if you were to observe a moon of such a large or of such a massive object, then the moon would look like this, and then it would simply orbit and give the impression that it's orbiting around nothing. Okay, so that's basically what you would see, and that's a very particular type of object. Some of you may have understood what that was. I'm talking, of course, about black holes. Okay, so more than 200 years ago, there was already premises of black hole physics by Pierre-Simon Laplace. So I think here it's a good time to end up this part on leaving the Earth and focus on one of the aspects that was very important for this mission, which was these gravity assist maneuvers. So what the hell are these things? To explain a bit what they are, I need to explain as well what type of trajectories can exist between any two bodies interacting via gravitation. Now, there are three types only of trajectories. The first one is simply a closed orbit that is an ellipse, basically like you see here. This type of orbit will occur when the object does not go fast enough to pay the cost of freedom, if you will. So it's not able to escape the prison of being bound to Earth. So the fact that this trajectory applies to every bound object, you could argue, seems to be contradictory to the fact that ourselves are not orbiting in ellipse around the Earth. Okay, we are simply stuck to its surface, and that's it. And so you could argue, well, then is it contradictory to what you just said? Well, no, it's not. Or yes and no. The reason why is because if you throw a ball, like this, for example, then you will see such a trajectory. Okay, so very typical, like bell-shaped trajectory, and this particular shape is the very familiar parabolic trajectory of a falling projectile on Earth. Okay, everybody, at least in the UK, learned this in A level, so in high school and even before, that this is a parabolic curve, etc. So you could even argue, well, it's not even an ellipse or anything. Well, it turns out that if you actually look at this from further away, and then you will see something different. It will look obviously like this, like what we have just seen. However, if you were to make, I don't know, to shrink instantaneously the size of the Earth, or make the ball transparent, not transparent, but basically go through materials and so on, then what you would see is that actually the trajectory continues to draw an ellipse that would go about the center of the Earth. Okay, so this is a very important point here, that the typical parabolic shape that we know of things we throw on Earth, they are just basically the representation or an approximation of a portion of an elliptic orbit, actually, that would go otherwise through the Earth and towards the center. So that's for the first case, and so that's close of the first case, that is the bound case. Now, there are two cases which have to do with having paid the cost of freedom. The first case is when you just barely paid the cost of freedom, and you have got no more energy after that. So the kinetic energy is exactly equal to the cost of freedom. In that case, you will find this particular type of motion. So the thing comes from infinitely far, and we go again infinitely far away, but the curve has this particular shape, which is that of a parabola. Okay, now in this case, the object is free, there is no problem, and interestingly, the curvature of this particular curve is such that you can think of it as an ellipse, the ellipse from before, being stretched up to infinity. Okay, so there's still like some remains, some remnants of this particular elliptic shape. The third case is when the object actually can afford the cost of freedom and more. So it has still some additional kinetic energy even after reaching infinity. And in that case, you've got some special shape as well. So then the object arrives and then moves across, of course, the Earth, and then goes back to where, not where it comes from, but basically it turned. There are multiple properties that are interesting for this particular trajectory. The first one, the object is free, of course, in the far past and in the far future. It is called a hyperbolic trajectory, and the thing here is that you can put two straight lines that are following the two arms of this so-called hyperbola. And what that means is that when you go far in the past of this particular event, then the object goes in straight line, and if you go far as well in the future as well, the object goes in a straight line, as if there were no forces acting on it. So these two events, which occur when the projectiles are free, are what are used for gravity assist maneuvers. The idea is to pick simply the right angle, the correct angle, etc., to get the right change of direction simply by going nearby a celestial object. And so it enables again to change trajectory without here using any propeller, and that's the reason why this is really useful for space exploration, and in particular for this 10-year mission, or in fact in reality 14-year mission, Rosetta mission. And so effectively this is really cost efficient. So this wraps up essentially what I had to do about what does that mean to leave Earth. This is summarized by this particular closed orbit. Then leaving Earth means that you take any of these two other possible trajectories, either the parabolic one, which is some kind of infinitely stretched ellipse, and then some other one which has some straight line arms that go far in the past and far in the future as well. Of course, this wraps up everything, because essentially now that all the gravity assist bits have been done, the only thing that remains is simply to reach the comet, and once this is done, then this is simple orbiting about it. So this closes the actual silver lining I wanted to use for this particular lecture, but I want, of course, to finish on discussing something bigger and grander. So what about travels far beyond the reach of the solar system? Well, I'm afraid that we haven't done anything like this yet. But of course, the goal is to think about what type of physics we know which could work to do these type of things. And here, general relativity, from Einstein general relativity, opens up entire new alleys for space physics. In particular, for example, there is this simulation here of a black hole. And what you will see is all the effects that occur, the light effects, the so-called gravitational lensing, and there are many other type of effects that you can't even fathom with the Newtonian bits that we have seen. And so there are many things that can be done there. Here this is for a black hole, which is a spinning black hole. So we see this is one of the fantasies, if you will, that was imagined more than 200 years ago by Pierre-Simon Laplace, and this is something that is being simulated and reinforced strongly by the theory of general relativity and, of course, very recent measurements of gravitational waves, and so on and so forth, that have led to Nobel Prizes. Now, this simulation is very interesting for what I want to say. Why? Because it's actually coming from a paper that was made by some of the people doing special effects for Interstellar. And this is an actual research paper to do that. So this is a mixing of the creativity and ideas of Christopher Nolan, mixed with the expertise of also Kip Thorne, who is now Nobel Prize 2017. That these two things that put together can give rise to fantastic narratives and great ideas, maybe, in order to move forward for space exploration. And so here I really want to close that by saying, yes, and this general relativity stuff needs to be explored in our fantasies, be it theoretical fantasies, but also fictional ones, so that we can really explore all possible ideas. And here I want to support this with a final quote, which is, "Imagination is everything. It is the preview of life's coming attractions." Okay, and with this, I thank you very much for your attention.